Okay, well, sorry about the slight glitch. I'm now very pleased to introduce Dick Lindzen, who's a professor emeritus at MIT. He's held faculty positions at Chicago and Harvard and at MIT. He's a world authority in dynamical meteorology with interests in climate, planetary waves, monsoons, planetary atmospheres, a very long list. And he's made seminal contributions to propagation of internal waves and gravity waves in the atmosphere, atmospheric tides, the Hadley circulation.
Okay, what do you do with that? Okay.
And he also, of course, knew Lorenz and Charney very well.
Yeah.
Thank you, Dick.
Thank you, John. Don't take my notes away. In any event, it's a pleasure being here, and it's always a pleasure to remember Jule and Ed. It's hard to know what I can add concerning atmospheric dynamics to what's been already said, but I'll give my gloss on it. And, meteorology as a scientific discipline, at least at the theory end, was traditionally divided into dynamic and physical meteorology. I don't know why oceanography put dynamic oceanography as physical oceanography, but those are the quirks of history. This is a picture of Jule. We were friends and occasionally went bicycling together, but one of the tortures I put friends to, we had a little studio in the basement for taking portraits. And I finally found this one. As Joe remembers, we had a house fire, so most of them were lost, but this one wasn't. In any case, if one goes back to the early period, before World War II, this is a terrific book I'd recommend to anyone for the state of the art of meteorology prior to World War II. And, it's actually very impressive. It has a lot of stuff by great fluid dynamicists, and the thermodynamics is very good. It displayed two approaches. I'm not going to be very precise about it, but there was work on meteorology by what I loosely call fluid dynamicists. People like not only Laplace, but Lord Rayleigh, Horace Lamb, Ludwig Prandtl, G.I. Taylor, Theodor von Karman. Interestingly, all of these people did contribute to dynamic meteorology. It was broadly understood as a source of meaningful problems. And then there were the meteorologists, and by no means a slouchy group. I mean, it's Willem Bjerknes, Sutcliffe Newt, it's K. Brunt, who wrote this book, Rossby, Bernard Horwitz, so on. And while the differences were not all that great, the dynamicists usually began with the equations of motion and systematically applied approximations appropriate to specific phenomena. The meteorologists typically were more descriptive and ad hoc in their approaches. I'll come back to that. Traditional meteorologists, and one of them has been mentioned several times, I was a little surprised, but in the history movies, was Sverre Pedersen. And he was almost entirely taxonomic. I mean, there was almost no dynamical thinking in the pictures he presented. Go through some specific examples, but it probably doesn't pay. At any rate, World War II was an extraordinarily important event for meteorology, apart from world history. It brought a lot of people into meteorology. And of course, as we've seen, Charney and Lorenz were among them. But so I would argue is Eliasson, Fjordhoft, Norm Phillips. There were some who didn't stay in meteorology, like Ken Arrow, who became a Nobel laureate in economics. But it turned out to be useful training, and he often referred to it. Anyway, Jule came to meteorology, as you've heard several times, via classical mathematical analysis. His advisors at UCLA, Willem Bjerknes and Jürgen Holmboe, brought him up pretty much to the state of the art in what was then dynamic meteorology. And Jule brought his mathematical training to bear on what was one of the major problems in dynamic meteorology, the origin of large-scale disturbances that characterized weather. It should be mentioned that his advisor at UCLA in the math department, T.Y. Thomas, may also have been important. I'm not sure of this, but I think this was the Thomas who did the first numerical study of the instability of viscous shear flow, the Orr-Sommerfeld problem. Wasn't him? That was a different Thomas, okay. In any event, he was interested in these problems. Jule's thesis on baroclinic instability in many respects represented a coming of age of dynamic meteorology. It occupied a whole issue of Journal of Meteorology. At any rate, what is that here? Yeah. This is it. This is the issue. It had a table of contents. I mean, it's unusual in an article, but it had quite a few things that were interesting in that respect. It included the math that Joe mentioned, and it was, how shall I put it, John Marshall looked for this on citation index, and it has a huge number of citations, largely from the mathematics community, which is a little bit surprising, but what I'd refer you to, of course, and this is what I had meant to speak on, when Jule died, we did prepare a memorial volume. And I would suggest to anyone who's interested, there are a lot of materials in this, including Joe's, I don't know, how would I characterize it, his loving description of the baroclinic instability paper. But there are also very nice reminiscences by Norm Phillips, Ed Lorenz, and there are, of course, George Plotzman's interviews, which were terrific, that, you got all these insights into how he looked at the field, how he related to it. At any rate, the article brought Jule to star status within meteorology. He had shown that the large-scale waves were instabilities on the basic vertical shear of the zonally average flow. And as has been mentioned, of course, in a rotating flow, the shear and the horizontal, the meridional temperature gradient are proportional to each other. At any rate, his approach was, I think, pretty much state-of-the-art hydrodynamic instability. I'd refer you to Joe's article in the memorial volume for details on this. As has been mentioned, the search for baroclinic instability was undertaken by at least two other meteorologists. Edie has been mentioned. There was also Halvor Solberg in Norway. And I think it's interesting to contrast the three approaches. Solberg began by assuming that the Norwegian polar front theory was correct and looked for the stability of perturbations on sloping frontal discontinuities. Having assumed this to be the appropriate question, he made no further significant approximations and found himself with a mathematical problem that he could not solve. Edie, by contrast, made insightful but ad hoc simplifications that allowed an almost trivial solution in terms of hyperbolic signs, cosines. Charney systematically approximated equations for a perturbation on a smooth mean flow, and this led to difficult but solvable system that furthermore offered a variety of insights and not just a solution. In this respect, Jule was closer to the world of the fluid dynamicists. The situation was, in fact, deeper than a simple difference in approximations. And here, maybe some controversy on this, but Eadie's approach suggested to many people that baroclinic instability was a kind of horizontal or slopey, slantwise convection. And I think that was misleading. On the other side, Charney and Stern in '62 showed that it was a variant of the traditional hydrodynamic plane parallel shear flow instability. And as Joe mentioned, later work by Peter Stone and Brian Hoskins showed that baroclinic waves led to fronts rather than the reverse. Now, any reasonable discussion of Charney's contributions to meteorology will take a lot more than 20 minutes, but I'll give you a few general remarks, and again, I refer you to the atmospheric challenge. I think the first thing we have to recognize is that we are talking about a very different era from the present, both for individual atmospheric scientists and for the department at MIT. Now, if you look at a list of Charney's publications, you'll see that they amount to about 60 publications. And by today's standards, that's a rather small number. I remember discussing this years ago with Joe, and Joe quite rightly pointed out, when we were grad students, the notion of 1 or 2 papers a year that were good should be a reasonable amount. Most of Charney's self-initiated, as opposed to invited papers, focused on explaining some specific observationally based question. That may seem obvious, but as we'll see, it's not so true today. They were attempts to answer questions rather than generalized studies. I mean, this is a matter of taste, perhaps. The questions included things ranging from the mutual interaction of hurricanes with convection to the explanation of blocking, to desertification, to Western concentration of the Gulf Stream, etc. Charney, and this has been mentioned already, he was rarely defensive about his attempted explanations. It was interesting. And I think he even enjoyed criticism as long as it made sense. I think it was also during that period, publications were regarded as communications, as opposed to canonical statements. Peer review is actually new at that time. It's a post-war phenomenon, largely. If you go back to the 19th century and read, the papers by Kelvin or so on, or even Lamb's book, these are discussions. Lord Rayleigh's collected works also. You would imagine, many of you, that you would be looking at more formal papers in that previous time. Quite the reverse, you're looking at conversations. And that's quite remarkable. Jule, as has been mentioned, always encouraged others. Almost always, Charney's papers branched into other questions. That was one of the remarkable properties. I think Jule was primarily someone who thought about the subject, in the following sense. It was common for Jule to use one paper to peripherally present thoughts on a variety of issues that others would have devoted many papers to. Indeed, Charney's papers were generally the stimulus for many papers by others, and even papers that were more general had specific practical aims. For instance, his paper on the scales of atmospheric motions, which developed the quasi-geostrophic approximation, and in turn allowed much progress in dynamic meteorology, I think was done to, filter gravity waves from the equations, so to enable early computers to stably integrate the relevant motions. His lovely paper on geostrophic turbulence explained why turbulence in a quasi-geostrophic system was actually closer to two-dimensional turbulence than three-dimensional turbulence, and allowed upscale cascade, as opposed to the expected downscale that was made famous by L.F. Richardson's doggerel. I think most of you know these, big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on, to viscosity. As we've seen, the little worlds work their way up in geophysics. Ray discussed yesterday, and this is one of the last things I'll come to, that perhaps Jule would have loved exoplanets. I suspect that Ray is right, Ray Pierre, but at least judging from the motivation of one of Charney's most important papers, his paper with Drazen in '61, what was the basis for that paper that he always stated? It was that his good friend from Princeton, the French astrophysicist Every Schatzman, had proposed the dissipation of waves propagating from below as a cause for the solar corona. And Jule was curious as to why the large-scale waves so prominent in the troposphere did not produce a corona in the Earth's atmosphere. This will be interesting both for its successes and for its failures in some ways. It led Jule, first of all, to become one of the first people to describe vertically propagating Rossby waves. And this doesn't seem like such a novelty today, but almost. Noting that such waves could not penetrate regions of easterly flow provided an immediate explanation why the extratropical stratosphere is azonal only in winter. In any event, the study also explained why the winter stratosphere is dominated by wave numbers 1 and 2. And in considering the origin of such waves, the paper offered a coherent argument for why orographic forcing is more important than thermal forcing in the production of stationary waves, a question that is still one which produces much confusion. Finally, they completed the work of Eliasson and Palm by showing why and under what conditions stationary waves satisfy the non-interaction theorem. The non-interaction of internal Rossby waves is in fact commonly referred to as the Charney-Drazen theorem, though it's sometimes subsumed under Eliasson-Palm. However, Bob Dickinson showed some years later that Charney and Drazen failed to show that internal Rossby waves could not reach the upper atmosphere. And it was still later shown by myself and Mark Schoberl that internal Rossby waves would nonlinear saturation would prevent their becoming a corona. Jule was very much the ideal citizen of meteorology. He played a major role in initiating numerical modeling, and we've gone through many of these things. We've gone through his role in Bomex, Gate, Figge, and this shouldn't be surprising. Charney, I think, said to Plotzman that a major reason for his move from Princeton to MIT was not just that von Neumann was dead, but he was motivated by the presence of a large observational effort at MIT. He was very supportive of what we were doing at Harvard during the 70s. He and his students at MIT, and the students at MIT in general, were essential to the success of our Tuesday evening seminars. We met at a Chinese restaurant and then went to have a seminar and discussions, and there was no time limit on the discussions. He also played a major role in the MIT Woods Hole Harvard seminars. And while these sometimes focused on things that today are of no interest, like why did Bénard convection form hexagons, they also included the early presentations of Lorenz's work. And this brings me back to the final comment on the very difference between that period and today's. At the time, I mean, there were only a handful of active departments of meteorology, and MIT's was clearly preeminent. There was absolutely no question I knew. Charney, Lorenz, and Phillips constituted a powerhouse in dynamical meteorology, but also Starr, Sanders, Newell constituted a powerful presence in data analysis. You also had radar meteorology, people working on instruments. There was also close relation with the experimental fluid dynamicists who were then in the separate Earth and Planetary Sciences department. It's not mentioned, but Ray Hyde was in that department for a while, so was Eric Malo Christensen. And then there were the connections with the mathematics department. I mean, people like Harvey Greenspan, Willem Malkus, David Benny, Lou Howard, C.C. Lin, Joe Pedlosky, K.K. Tung. etc., all of whom were deeply involved in the problems of rotating flows, convection, hydrodynamic instability. The geophysical fluid dynamics at times seem to be at the forefront of applied mathematics at MIT. There were several groups at private centers as well as the Air Force that regularly participated in MIT seminars. One would, moreover, be remiss if one didn't mention Henry Houghton. He was not, I think, in the same league. He did cover radar and some radiative transfer. MIT students often registered at Harvard for Richard Goody's course in radiative transfer. Students at Harvard often took dynamics at MIT. Cross-registration was easy. But as chairman of MIT's department, he was extraordinarily successful in building up the department, and sometimes not mentioned, but he also played a major role in the creation of NCAR, the National Center for Atmospheric Research. Today, there are many departments dealing with the atmospheric and oceanic sciences, but the emphasis tends to be not so much on specific phenomena, but, for instance, the role of putative climate change. Studies are, I think, when I look at the journals, far more common today than explicit problem solving. MIT itself has a very small effort in observational meteorology, and analysis is much more likely to be of model outputs than of actual data. On the more positive side, the absorption of meteorology and oceanography into what is now the Department of Earth, Atmospheric, and Planetary Sciences is now unified in enlarged oceanographic work. On the other hand, relations with fluid dynamicists in the rest of MIT have been significantly reduced, as have GFD activities in the math department. So have interactions with other institutions. Part of the reason is that academic scientists have to spend much more of their time raising funds. For many years, meteorology was supported at MIT by group grants that were renewed on the basis of site visits. Paperwork was much less. There was a certain leisureliness that was implicit in the close interactions with Harvard and the Woods Hole Oceanographic Institution, and that leisureliness is now much diminished and undervalued. How all this will work out in the future is, of course, hard to tell, but fortunately, there remain many crucial problems to be solved in atmospheric dynamics, leaving much for future Charneys and Lorenzes to work on. Thank you.